So how are you guys doing today? It's so nice to meet you guys face to face. Are you guys from the same school? No, different schools. Do any of you know anyone? Only two? Another pair? Nobody else? But all of you are from NYU, right? School in NYU? No? So you guys are from different, the high school you went to, or you are going to. Yeah. You all are in high school, right? Yeah. And you're also taking this class. Yeah. Are you taking any other classes? Or only this class? Only this class? How are you feeling? How do you feel about college life? Okay. So do you have class during the day and you're taking this class at evening? Yeah. That means if you do online classes, you will be great, right? Because you don't have to come here from your school. You can directly go to your home. My school's in you can simply. Cool. Wow. If I were in high school, I definitely wouldn't want to be in college at the same time. I actually never took any college classes when I was in high school. I took calculus in my high school. So, normal calc. And in my high school calculus class, there are only 8 students, I think, in that class. So it was very short. But yeah, we learned a lot in high school. So, what do you expect here? Like, what is your expectation? Why did you sign up for this class? Like, what was it? What is your goal? I guess I just wanted college. I always knew that math. Cool. So if you take this class and you pass, you don't have to take this class again when you go to college? I think so. Depends on college? Yeah. So I don't have space. Are you guys all a senior here? No? You're not senior and you're taking this class? Wow, what grade you are in? Junior? Yeah. 11, right? Yeah. Wow. Anyone else? Is there any freshman here? I hope not. Freshman is too early. How about sophomore? Any sophomore here? No? How about junior? How many junior I have? Wow, a lot. And rest of you are senior? Cool. I respect you guys a lot. I never wanted to like go beyond my level. So I was like, I take my time to do things because I don't have any rush. So you guys are rushing to your career. It's amazing. Keep up the good work. Now, any questions before we start? Any comments, concern, complaint? Any complaint about online classes from anyone? Don't be afraid if you have any problem. I'd like to know what is the problem and how can I help you with that. No one has any complaint? No? Wonderful. Guess what? Our next class will be online. Today is Wednesday, right? 5th. So, today we are here on 5th. Our next class will be online. And our class will be a little shorter in 7:20 because I have another conference to go to. And then Wednesday we have the class. When is it closed? Next Wednesday. And then when you come back, Monday there is no class. See? No class. But guess what? Tuesday will be a Monday schedule. So instead of coming here on Monday, you're supposed to come here on Tuesday. But you're not going to come here because our class will be. Okay?
But if we're unable to make it here on Tuesday, we're not here for like class on Monday, Tuesday.
I'm going to record the class. So if you can't make it on Tuesday, I understand because messed up schedule. Can you always have this messed up schedule every semester? So if you cannot have no problem, just watch that video. No problem. And if you guys have no issue about online learning, then maybe we have more online classes if you would like. But definitely these two has to be online because I have much of access. Okay. And I told you about myself, right, at the beginning of the semester. So let me tell you again for new students. I'm actually doing PhD at Columbia, and I'm doing my PhD on magnetic field. So I did my bachelor at CCNY at the City College on applied math, and then they didn't have any more applied math. They have pure math, which is like completely different than applied math. So pure math is about why things are happening, and applied math is like how we do things. So from one field, I went to another field. That's because they didn't have any applied math. So I did my pure math. I did my master's in pure math, and then I took a few years off, 1 or 2 years, and I was like, well, let me do something different, what I like. So when I started teaching, I realized, oh, I love teaching. So I was like, well, let me do something on teaching. So I started my PhD on math education. It's like learning math, how to teach math. Okay, so I'm learning how to teach better. So since I'm a student myself, so I understand your pain. So I'm trying my best to make this class as easy as possible. So if you notice, I actually uploaded the lecture slides on Brightspace just today, few hours ago. So all the notes you have, whatever I'm going to go over in class, now you have them on Brightspace. So if you want to download them, print them, you can print them, but don't print one page per slide, one slide per page, because it will be a lot. See, 111 pages. So if you can print 4 or 6 slides in one page, it will be smaller. It will look smaller, but actually it will be visible to you. So you can print them, and if you don't want to write down any notes, you can simply bring them in class and write down whatever math we do here instead of writing down all these big things. And also, I'm not following the order, the chronological order, like 1.3, 1.4. I mixed everything up because I wanted to have all the topics together. Like limit has different topics. So far we did 2 topics. One was the normal limit, when you just substitute everything, we get a real number and stuff. Second topic we did was when you substitute, you get a number on the top, 0 on the denominator, it means you're dealing with vertical asymptote. So to find the limit at the vertical asymptote, we use different approach. And then we have a third scenario where on the substitute, you get 0 over 0, something totally undefined. So we have few more steps to find the limit for those cases. So I wanted to put together all those limits, plus we have one more limit, like when x is too big on the left or too big on the right, what happens to the y values? So I wanted to combine all 3 types plus that extra infinite limit together and then have continuity. Okay, so that's why I'm not following the order in the book. I'm following my topic. So whatever I have, I don't have any section number. That's why at the beginning of the note, I wrote down all the sections, what sections I have in this lecture notes. So if you take a look at the homework has actually different questions in each section. So I didn't put any deadline yet. Probably I'm going to put down fast deadline next week, somewhere next week, either Monday midnight or Wednesday midnight, something like that. Okay. So you can start doing your homework. Once you're done with all 4 sections, then I'm going to close the homework date, and then you'll take a quiz on my MATLAB. So my MATLAB is at Baruch. I'm also teaching at Baruch, and they're using my MATLAB and other software. You're using Lumen. So you're going to take a quiz on Lumen, but it's not an in-class exam. Once you're done with chapter 1 and few sections of chapter 2, let me see which 2 sections. Here. 5 sections. So when you're done with chapter 1 and derivative, then you're going to take our exam 1 here. And I'm hoping to take our first exam on March 26. February 26th. It's like 21 days from today. So before the exam, I'm going to post a review sheet. If you study the review sheet very well, you can do it in your exam. Any question? No? Then let's start. So do you remember what is vertical asymptote from our last class? What is vertical asymptote? Go ahead. You. When our denominator is 0, so denominator 0 means we have undefined y value. So when the denominator is 0, we don't have any y value. As a result, the graph breaks apart. So vertical asymptote is the point where our graph breaks apart. So when our graph breaks apart, either we have the limit positive infinity or negative infinity, or it doesn't exist. So in our last class, we did your example, for example, here 1 over x, when x is 0, the y value doesn't exist. As a result, exactly at 0, there is no y value. However, if you get close and closer to 0, from the left side, your y value gets very smaller. So limit is negative infinity. But if you go to 0 from the right side, our y value gets bigger and bigger. So we get positive infinity. So one-sided limit from the left side is negative infinity. The right-sided limit is positive infinity. And if both limits are not same, then limit exactly at that point doesn't exist. So that's why the exact limit doesn't exist, but the one-sided limit will always exist. And if you have your left side limit and right side limit, they are the exact same limit, then your exact limit at that point is the same limit as your left and right side. So we did few examples in our last class, and we ended up with piecewise function. Now, piecewise function is not same as a function which has vertical asymptote. The difference between limits of the piecewise function and limits of the vertical asymptote is that for vertical asymptote, the limit at the one-sided or exact, it doesn't matter, will be either infinities or doesn't exist. On the other hand, piecewise function, it means you have different pieces of function gluing together in one xy plane. So you have different functions, not one function, different functions. So for each function, we substitute the number depending on what function we have up to that domain. And then we have left side limit, right side limit as a number, not as infinity. They are number, left side limit and right side limit. And if left and right side limit are not the same number, then the exact limit doesn't exist. So piecewise function doesn't have infinite limit. It has a number as a limit, and either number or doesn't exist. And we did one example in our last class where we had two pieces. One piece of the rational function, the other piece was a parabola. So parabola and rational gluing together at 2, and we found that the left side limit is 1, the right side limit is -1. As a result, exactly at 2, the limit doesn't exist because we have a jump in our y values. Can you do this by yourself based on what you did in our last class? So try doing this by yourself, and let me take your attendance. Kimberly? Patty? Yeah. Patty, right? Okay, here it is here. Judy, Mac, Jihad, Jihad, Ziad, Hamid. It's G or Z? Z. Chi, Chi Mai, Chi Mai Huang, Jocelyn, Anjum, Anjum Khan, Lucas, Hoy, Logan, Hoyer, Ellen, Musfika, Nicholas, Sanzin, Sian, Sion. How do you pronounce it again? She. Okay. Raka, Ella, Apollo, Andy. We are very fast in-person class, and 4 people are missing. But in case you are here in last 2 classes, all of you are here. That means they prefer online more. Are you guys done? Great. So who would like to help me with the first one, left side limit? Any volunteer? No volunteer? Go ahead. Lucas, right?
Nothing much. X, we substitute anyone to math on one.
So limit x goes to 1 from the right side of the function to minus x. And then what did you do? So 2 minus 1, 1. Did all of you have 1 for this one? Got 1? Okay. Who would like to help me with the right side function? You want me to call you Sanzim?
Second equation of x over 2 plus 1. So once you plug in 1 and 2, get 1 over 2 plus 1, which equals to 1.
X over 2 plus 1. Then oops, wrong. You substitute 1 to x. We get 1/2 plus 1. That gives us 1.5. So our left side limit is 1, right side limit is 1.5. Then what happens to the exact limit? What is our exact limit? It doesn't exist. Did you notice most of the piecewise functions, where they break, actually the exact limit doesn't exist there? Did you notice that? It's not always the case, okay? It's just that the example the book gave us, or the example from where I got those examples, they have all the examples where the exact limit doesn't exist. With this, we are done with piecewise, and now we are going to our third scenario. In this scenario, after you substitute the limiting value into the function, we get 0 over 0, which is completely doesn't exist. It's undefined. In this case, we did the exact same thing what we did, not exact, similar things what we did for case 2. First we substitute and see what do we get. If it's 0 over 0, we have to modify the function. It means if it's factorable, factor and cancel. If it's rationalizable, then rationalize. If you're working with trig functions and you can apply trig identities, apply the trig identities. So do something so that you can modify the function. And once you modify the function, you get a new function. And then you resubstitute your limiting value into the new modified function. And whatever you get, that's the limit. Okay, so 3 steps. Let's start with something like this, where we have an absolute value function on the bottom and a line on the top. So absolute value, if you remember, absolute value actually has 2 parts. What type of graph absolute value function has? Do you remember? V. Okay. So this is the scenario what is happening. Oh, do you need time to copy the left page? Yes. Okay. So in absolute value function, it's a V shape. And if you observe, actually this V has 2 equations combined together. One side is positive and the other side is a function going down. So one is increasing line, the other one is a decreasing line. So absolute value is a combination of 2 lines. That's why they become V. One line is the increasing line, one line is the decreasing line. And they meet at whenever this function is 0. So this function is 0 when x is -9, right? So at -9, before -9, our function is a negative linear function. The same function but negative sign. And after 9, this function is a positive linear function. The line is going up increasing. So this is positive x plus 9, this is negative x plus 9. So when we find limit, we have to consider both scenarios. We have to break them down into 2 pieces. One is what is happening before -9 and what is happening after -9. And then we see, do they have the same limit? So limit x goes to -9 from the left side, and limit x goes to -9 from the right side. So this is -9. Before -9, our line is going down. So this portion is negative x plus 9. And after 9, this line is going up. So this is positive x plus 9. I'm only observing the denominator because denominator has absolute value. So when you break down into 2 pieces, our denominator will have 2 pieces. Anything before 9 will have, without absolute value, the original line with a negative sign. So negative x plus 9. And after 9, our denominator is the positive portion. So it's positive x plus 9. Numerator is not getting affected by that. So we keep our same numerator. Numerator doesn't have an absolute value, so we just bring this down. Any questions so far? Did everybody understand what I did or why I did these 2 steps? You guys are okay? Great. So now we are going to modify them. How can we modify the functions? We can factor 6 from the top. So if you factor out 6 from the top, we get what? X plus 9. X plus 9. And we still have same denominator. X plus 9, x plus 9. Is this right a little bit above? Now what do you observe on the top and on the bottom? They cancel, but we cannot just leave them alone because we still have 6 on the top, negative on the bottom. So what do you have? So this is -6. Oops, my bad. -6. So left side limit gives us -6 as the y value. And what is happening on the right side limit? What do we get? Only 6. So left side is going downward on the -6, but the right side is going upward on +6. So we are finding the exact limit exactly at 9, -9 of this function. What is our exact limit? Doesn't exist. Too bad. We have another example. Doesn't exist. You will see this question again in the homework. Any question? Was any step unclear or confusing to anyone? You sure? So this is what I wanted to show you before. The purple line is the line y equals x plus 9. And the green line is negative y equals negative x plus 9. Now, wherever they intersect, only the above portion gives us absolute value of x plus 9. So that's why when you pull out the absolute value, we get two pieces, the green piece and the blue piece. The red piece, the green piece is left side limit, so you get negative of the absolute value. And this side is the positive, so we get positive x plus 9. And then we simplify each of them. Okay. Now, what do you think about this one? What is our step 1? True, but whenever you evaluate any limit, what is the first step always? Substitute and see what type of limit you're working with. So go ahead, substitute and see. What do we have? X squared minus 9, then you have 2x squared plus 7x plus 3. Then negative 3 squared minus 9, 2 times negative 3 squared plus 7 times negative 3 plus 3. What do you on the top? How much is negative 3 squared? 9. So we have 9 minus 9. And do you multiply 2 times negative 3 first, or do negative 3 squared first? Negative 3 squared. How much is negative 3 squared? 9 times 2. 18. How much is 7 times negative 3? Negative 21. And how much is 18 minus 21? Negative 3. And negative 3 plus 3? 0. So what do we have? 0 over 0. 0 over 0 means modify your answer. So modify your function. If you had number over 0, that means it's one-sided limit. But if it's 0 over 0, means modify. Now the question is, how can you modify? So someone told me it's perfect square, so I difference perfect squares. So limit x goes to -3. We are going to factor this. We are going to modify this by factoring. What two factors we get on the top? X minus 3, x plus 3. How about the bottom? We can factor by grouping. Let me do it on this side. So we have 2x squared plus 7x plus 3. How do you factor by grouping? What do you do? 6x plus x, 2x squared plus 3. Why did you pick 6 and 1? Why did you pick 5 and 2? Or 4 and 3?
Expressions that are 6 and 1. We have a 2 6 6 and 3. But you have to make sure that we'll just go some next.
2 times 3. So that's the hint. Anytime you have a number in front of x squared, you have to multiply that with your constant. So 2 times 3 gives us 6. Why should I write somewhere here? So this is called AC method. Another name for grouping method is called AC method. So you actually start from here, multiplying A and C. And then you split that into two pieces, the middle term. When you multiply them, when you combine them, it has to, you're going to split this into two pieces. When you combine them, it will turn into 7x. So I cannot use 5 and 2 because 5 times 2 is not going to give us 6. We have to use two numbers. When you multiply them, we get the 6, the AC. So only 6 and 1 will work here. So it's split 7 into 6x and 1x. Okay? So do you guys know your grouping method? You all know the grouping method? Cool. So we have 4 terms, so we're going to group. What do we have in the first group in common? 2x. Once you pull out 2x, what do we have? X plus 3. And what do you have common in the first group, second group? 1. So you bring down the sign, whatever sign you have, you bring it down, and then you group the other part, x plus 3. And then what? What do you see in common? So both groups still have x plus 3. So we pull out x plus 3, and then we have 2x plus 1. So denominator gets x plus 3 and 2x plus 1. Let me show you something new. Which I found amazing. Okay, so most of the college students here, not only here, wherever I taught. So I taught City College, Hunter College, Baruch College, Max University, I taught Fordham University, and I noticed that people actually hate AC method. People hate the grouping method. For some reason, they find it hard. Why? Because if A or C, one of them is big, then when you multiply them, you get a bigger number, right? So it becomes harder. So what actually people found out is that instead of grouping, you can factor directly, just like these two binomial, instead of doing all this hard work. If you do a trick, the trick is this. You multiply A with the C, no problem. So you get 2x squared plus 7x plus 6. Instead of writing 3, you write 6, and you erase your first term. Okay? So they rewrite this equation by not writing A, and instead of writing C, they write AC. And then you factor. Normal way. Two numbers multiplied to 6 combined to 7. What are the two numbers? 6 and 1. So plus 6 plus 1. Well, it would have been the result for this polynomial, but the thing is, we do not have this polynomial, we have this polynomial, right? So that means you have to do something to connect this polynomial with this polynomial. So what they do, they take this coefficient and divide everything by 2. Not everything, all the numbers. This number by 2, this number by 2. So they have x plus 3 and x plus 1/2. Now you may wonder, well, we have x plus 3 same, but these two are not same, right? Well, these two are not same because this is not in factored form, but this is in factored form. Okay? So in fact, fraction. This is not in fraction form, but this is in fact fraction form. So this one you can actually rewrite as, if you multiply top and bottom by 2, you get 2x plus 1. Okay? And you just ignore the denominator too. If you didn't understand, it's okay, you don't have to understand. But eventually, when you end up getting big numbers to work with, you'll actually appreciate this method. And this method is especially helpful if you're solving for your x. So if you solve for your x, you get 2x plus 1 equals 0 from here. So you get x equals negative 1/2, right? And in here, x plus 1/2, 0, you directly get negative 1/2, the same answer. So they look different, but they're actually the same expression. Okay, Neil, going back to our original limit. So what do you do after we factor them? What do you notice on both top and bottom? X plus 3. So we cancel them. And you write limit x goes to negative 3 of x minus 3 to x plus 1. So we did step 1, substitute, and see what type of limit you're working with. Step 2, modify. What is our step 3? What do? Resubstitute. So we are going to substitute x with negative 3 again into the new simplified version. So we get negative 3 minus 3, 2 times negative 3 plus 1. What do we have? Negative 3 minus 3. Negative 6. 2 times negative 3. Negative 6 plus 1. So negative 6 over negative 5. And what happens to the double negative? They turn into positive, so it becomes 6 over 5. So this is our final answer. So this function has a vertical asymptote at x equals negative 1/2. So at negative 1/2, it will break into 2 pieces. And later, I'm going to teach you that whatever we cancel, that cancel term actually leaves something into the function. What it leaves is a whole. So when x is negative 3, we don't have a y value. We have a whole. That's why we are finding the limit. When x is negative 3, what's the limit? The limit is 6 over 5. The limit is 6 over 5, but the y value is not 6 over 5. Why not? Because the y value doesn't exist yet. It is a whole into the function. And that whole, we call them removable discontinuity. So we have different types of discontinuity. One is the vertical asymptote, where the graph is not continuous. So we cannot remove discontinuity anyhow. So it's called non-removable discontinuity. But whatever we cancel, that will leave a hole into the function. And we can close this hole by plugging y equals the limit and make it as a continuous function. So we call them the removable singularity we call them removable discontinuity, the hole, because we can have tricks to complete this hole into a filled hole, into a closed circle. Not now, but later we are going to learn about these details. Another example. Oh, any question on the last one? Anytime you have any question, please don't hesitate. I don't want you to feel shy around me. See, I'm definitely not gonna laugh at you. You can see already by seeing me, right? I smile a lot, but I definitely don't laugh at students' questions. Okay, so you can ask me any question, even if you think it's the silliest question, no problem. I ask my teachers a lot of silly questions, and one day she complained, "You ask so many questions, good thing, but all of your questions are silly questions." So I'm like, well, what can I do? So what type of limit here we are dealing with? What do you see? What is our first step to figure that out? Substitute. So did you substitute? What do you have? 0 over 0. So that case, so for 0 over 0, you have to modify, right? So let me conjugate. Good. So let's do the first step. We have 9 plus 0 minus 3 over 0. That gives us square root of 9 minus 3 over 0. That gives us 3 minus 3 over 0. That gives us 0 over 0. 0 over 0 means modified. So the last question we modified by factoring. This question we cannot factor, but we are going to do rationalize. Rationalize. We are going to rationalize the numerator. When you rationalize, the same expression looks different, but they are the same function. They just look different. And as a result, when you resubstitute, we are going to get something valid, not something invalid. So we have 9 plus 8, another square root, minus 3 over 8. And how do you rationalize? Do you remember your rationalizing steps? Rationalize means don't somehow get rid of the radical. So we are going to rationalize the numerator, means we want to see this radical on the top. We want to bring this radical on the denominator from the numerator. So we use a concept called conjugate. So what's the conjugate of the numerator? Huh? Anyone? Nine and what? 9 plus 8 plus 3. Why you are not sure? Why you are not confident? But you did it perfectly. So conjugate only changes one sign. Okay. So we have this term is one term and 3 is another term. Conjugate means keep the two terms same, just change their middle sign. So the negative 3 will turn into positive 3. And we have to keep the first and second term exactly same as they are. So you cannot put in 9 minus h. It has to stay as plus h. So we multiply both top and bottom by 9 plus h plus 3. And then what happens when you multiply two conjugates? You have two ways to find that out. One is FOIL them out and then see what you get. Which method I dislike? Because the purpose of conjugate is to apply that knowledge. When you have difference of product squares, how do we factor them? We add the two bases and subtract them, right? So what do you observe? x plus 3 and x minus 3, what type of relationship they have? Because, yeah, but
You're creating the difference in squares by multiplying.
so
You're-
conjugate.
So your square, your first term minus.
Exactly. That's why we use conjugate. Because when you multiply any two conjugates, the result is the first term squared minus the second term squared. Yes, you're allowed to use FOIL, but why you are ruining your method by using old school method? Okay? Where you can simply take the first term square this minus take the second term square this. That's it. So our first term is square root of 9 plus h, and you're subtracting second term. Both of them, all you have to do is square them. That's the purpose of conjugates. The product of conjugate is their individual square, the two terms. Can you do anything on the denominator? What do you think? No? So leave them alone. Do not distribute. And now what happens to the first term? Square root of the square. What is square root of the square? What happens? Cancel them. So whenever you have radical and its power at the same time, they fight with one another and they will die. So you don't see them any longer. We see only 9 plus h. And what is c squared? 9. And we have the same denominator, 9 plus h plus 3. What do you observe on the top? 9 and 9 cancel out, plus 9 minus 9. So you're left with h only, and then h, 9 plus h plus 3. And now what do you observe? Of course, this h is multiplying with that, and this h is single. So anytime you have multiplication or single h or single anything, you can simply cancel them. So I don't have space, let me write here. On the bottom, we have 9 plus h plus 3. We had h on the top, but it canceled it. So now what do you have on the top? 1. Whenever we don't have anything, in multiplication or division, we always have 1. So that expression and that expression, they are actually exact same two functions. So if you graph them, you will see they are exactly the same thing. However, something is different. Observe what happens when you plug in the limit here. Limit h equals to 0 of 1 over 9 plus h under the square plus 3. Oops. We get 1 over 9 plus 0 plus 3. 1 over square root of 9 plus 3. What is square root of 9? 3. And what is 3 plus 3? You see? Cool, right? They are exact two functions, they look different. And when you substitute h 0 here, you get something invalid. But the same function, if you substitute here, you get something valid. Cool, right? So in our real life, we face this type of scenario many times, where if you walk in one direction, it ends up getting nowhere. So you modify your direction a bit, and then you go to your goal. You get the same result. Okay? For example, you want to be happy in your life, right? So your goal is to become happy. And now you have two choices. Either you take harder path to become happy, or you take shortcuts to become happy. For some people, shortcut is easier for them. For other, shortcut is not easy. We have to have a hard life between our goal and between our present life. So we face many hardships and eventually we become happy. Unlike some people who they are always somehow they become happy easily. Okay? Because our life is unfair. The same thing here. H wanted to be in the function, but it couldn't because the final result is invalid. So we made some path for the H to get into the function, and now it becomes happy. It gives us some valid number. Any question on any step? Was anything unclear to anyone? So I showed you 3 examples. One with the absolute value, one with normal substitution, while you have to factor and modify. Here you rationalize and modify. Okay. So now you have enough knowledge. Go ahead and do this by yourself or with your neighbors. Try these 4 questions. I'll give you around 10 minutes, 12 minutes. What do you think? Can you do them in 12 minutes? Great. So it's 6:28, 40. At 6:40, we'll do them together. You don't have to work alone. You can talk to your neighbors. Uh, 17. P. Chimai. No. Anjum. No. Is there anybody whose name I did not call? No. So conjugated plus count, new second term with a middle section. So it was 9 plus 8 plus 12. And minus, so plus. Compose by you? So this is the one. So for this function, when your x is one, you don't have any nothing, you don't have any value to limit. So when you modify, you're getting rid of the extra portion which causes the problem. So once you get rid of the problem, you start to that tells you the value. So it means when you move from the left side and move up on the right side, they go to exactly on which one makes sense. So you're supposed to have a y equivalent to one, but you don't have a equivalent to one because that's one that really just the y is supposed to be. The y is supposed to be a two marker. Yes. Here we don't see that there's something wrong. So by factor, we see that there's something wrong. So we get into the conclusion. And for the right that we really want to, we find the limit based on that input. So whatever it kicks out by canceling, that's supposed to be why they will give us for this example. But since you kicked it out, it left from the zero function. So you don't get the right value. So this whole is the part that's not one. We kicked it out, so we don't have any y value. We have a y value for the rest. And the limit is telling us, well, come up from the left side and go up from the right side. At that point, at that point, one, your y value is one. So yeah, but the thing is like always I mean, I really don't know. We have to see when you substitute x equals one in here versus y value. So this is one, yeah. Thank you. So it's down there. Oh, um, so you multiply it up and multiply. So you have minus one. Rewrite the progress here. Rewrite that. It's a drafting one. Right, so just modeling to often allow minimum. Yeah. Multiply is by exponent. Is up to the second perfect. Ready? Okay, so the first one, when we factor the top, we get x minus 3, x minus 1, right? And when we factor the denominator, we get x plus 1, x minus 1, right? So visually, if you want to see what is happening here, we graph x plus 3, x minus 3, x minus 1 over x plus 1, x minus 1. It's the red one here. So once you graph, we notice that, well, they both have x minus 1 in common. So it cancel, and then we're left with x minus 3 over x plus 1. Now look what type of graph we have for x over x minus 3 and x plus 1. You see that the exact same graph. The red graph is covered by the blue graph. It is the exact same graph. So what's the difference between these two? The only difference is the thing we kicked out. We kicked out x minus 1, so that gives us x equals 1 when we set it equals 0. It means when our x is 1 here, we're supposed to have a valid y value, but actually we don't. So if I take the original one, Desmos doesn't show it, but here we actually don't have any y value at 1. When x is 1, here y is negative 1, negative 1. So annotate it. Okay, so oops, sorry, my bad. Here. If you use a graphing calculator or something better than Desmos, you will see that here we have a hole. So the original graph doesn't have the hole, but this graph does. The blue one. The red one doesn't have any hole, but the blue one has a hole. Why blue one has a hole? Because in the blue one, we kicked out x minus 1. So from the red one, we kicked out the x minus 1, we got the blue one. So we had a hole. Since we kicked it out, it got so angry. It says, well, if you're kicking me out, I'm going to leave some problem for you. So the problem it leaves us is the hole. So the limit, what limit is telling us? Limit is telling us that, well, even if you don't have a y value there, we don't care. We have a limit that's supposed to give us the y value there. We don't have the y value, but we're supposed to have that y value, what we got from the limit. Okay? So now do you understand the conflict between the original version and the modified version of the function? Okay, then let's do them together. Come on, go down, go down. Okay. So step 1 is always substitute and see what type of limit. When you substitute, we get 0 over 0. You checked it, right? 0 over 0. Since it's 0 over 0, it's time to modify. X goes to 1, we have x minus 3, x minus 1, x plus 1, x minus 1. We kick out x minus 1, and we get limit x goes to 1, x minus 3, x plus 1. We re-substitute, we get 1 minus 3, 1 plus 1, that gives us negative 1/2, which is exactly the same thing what we seen in the graph. So it is supposed to be the y value for the number we kicked out, for the limit we have 1. So it was easy, right, the first one. Now, second one, once you substitute, you see again it's 0 over 0. We did it, right? So we did question 2 already. Wow, I didn't realize that. I meant another question, but yeah. Then let's do this one. Since you already did that, let's skip that. And this one, when you substitute, we have 0 over 1, 1. That gives us 0 over 0. So it's time to modify. We have, actually for modifying, we don't have to write limit. Let's skip that. So we have 1 minus x minus 1 plus x. Now, what you're going to multiply by? What's the conjugate of the denominator? Any volunteer? Apollo. Perfect. So as I said before, conjugate has only one thing changed. It's the middle sign between the two factors, between the two terms. So you multiply top and bottom by the same thing. So the top stays same, 1 minus x plus 1 plus x. And what happens to the bottom? So 1 minus x squared and 1 plus x under the radical, they get square. But anytime we have radical and square root and square, they cancel out. I'm too lazy to write down the numerator again, so let me just draw an arrow. Numerator stays same. And what do we have on the denominator? We have 1 minus x from the first one. And how about from the second one? Please don't do this. 1 plus x. Give me 1 second. Is it like this? Almost perfect. You have to parentheses. Because anytime you subtract more than one term, the sign will change for the term you're subtracting. So you must have to have a parenthesis. So we are going to distribute the parentheses. That will tell us that we have 1 minus x minus 1 minus x. So what do we have at the end? What happens to the plus 1 and minus 1? Cancel out. And what is left? Negative 2x. So now let me write this down again. We have limit x goes to 0. The top is this. 1 minus x plus 1 plus x. On the bottom, we have negative 2x. So you modify the original one into this piece. Now what do you see? We can cancel out the excess. Once you're done with excess, we can substitute our 0. So 1 minus 0 plus 1 plus 0 whole thing divided by negative 2. So square root of 1 plus square root of 1 divided by negative 2. What is square root of 1? So 1 plus 1 over negative 2, 2 over negative 2. The answer is negative 1. So Apollo, do you have negative 1? Do you? How do you have negative 1 if you made the mistake there? So you subtracted without using parentheses. Then why you told me it's x plus x? You could tell me it's minus x. Okay, I'm glad you found a mistake. So, anybody has any question on this one? Was any part confusing? Unclear? No? Okay, the last one. Last one is interesting because you don't get a number. Why? Because we have an extra variable to work with. X is a variable and our limit is based on the 8, not on x. So 1 over x plus h squared minus 1 over x squared. And instead of writing down everything by 8, let me just put divide by h so that I have more space to write them down. They're exact same expression, right? The top divided by the bottom. So instead of writing top by bottom, I write top divided by the bottom. Now, how can we modify the top? What can we do? Anyone? Go ahead. Factor. How can you factor? Combined fraction. So we need the LCD. What is our LCD? X squared times x plus h squared. So what is missing on the first denominator? So we multiply top and bottom, the first one by x squared and the second one by x plus h squared. So x squared minus x plus h squared, and they are dividing by h. Great, first step is perfect. Then what? Expand, great. So we have x squared. When you expand the second term, what do we get? X squared plus 2xh plus h squared. And when you pull out the parentheses, what do you get? X squared minus 2xh minus h squared. And from here, negative 2xh minus h squared. I'm skipping the denominator because I want to fit everything on one page, but we actually have to keep writing the denominator for every numerator. I'm getting lazy. So let's continue here. We have limit h goes to 0, and we have on the top negative 2xh minus h squared, and on the bottom we have x squared plus, on the bottom we have x squared and then x plus h squared, and this thing is dividing by h. Right? So this is the simplified stuff, but we still have our same denominator. And we still have dividing by h. Now, what do you observe on the top? You can actually pull out an h first in order to cancel with the dividing by h. So if you pull out an h, you get negative 2x minus h, x squared, x plus h squared. And dividing by h is same as multiplying by its reciprocal. Right? Anytime you divide by something, it means you're multiplying by its reciprocal. So dividing by h turns into multiply by 1 over h. Why we did that? Because we can cancel this h on the top with this h on the bottom. So finally, we have limit h goes to 0, negative 2x minus h, and then x squared, x plus h squared. So now we have a simplified new function. We did everything else. We are done with our modifying. What do we do now? Substitute. So you replace every h, only h with 0. What happened to the x? We have to keep them because they didn't tell us what x is, what are the number for x. So you get 2x minus 0, x squared, x plus 0 squared. What is x plus 0? X plus 0? X. So we have x to the square. And then what? What do you see? The 2x on the top, and then x squared on the bottom. We can add the bottom, okay. So 2x over x to the 4. One of the x cancel with one of the x on the bottom. Question or answer? Negative, negative, yeah. I missed my negative. Thank you for pointing this out. So in division, we subtract the power. So we have -2 on the top and x cubed on the bottom. That's it. We have nothing else to do. What is 2? Yeah. Question. Was any step unclear? So how it would look like in the graph? Let's see. We have -2 over x cubed. This is the graph. It's a graph where we have vertical asymptote is 0 because when x is 0, the denominator is 0. The graph breaks according to two pieces. Point is 0. Before 0, we have one piece. After 0, we have another piece. So it's like 1 over x, but it's more slant, more line down than 1 over x. Any question? Okay, so now we know how to modify 0 over 0. So all the things we did, first scenario, substitute, get a number, done. Second scenario, vertical asymptote, means one-sided limit. The result is either infinity or doesn't exist. And then we talked about piecewise function, where we did one-sided limit by substituting into each piece of the function separately. And then last thing we did was 0 over 0, means modify either factor or rationalize. And then do we have trig? We have trig later, not now. The next one is an interesting function. Greatest integer function. We write this, we like this, x with double brackets. So this is a picture of a graph. What it does is that anytime you plug in any number here, that is not a whole number, it goes down to the whole number. For example, if you have 4.8, it goes down to 4. It doesn't go up, it goes down. When you have pi, how much is pi? 3.14, right? So see, pi goes down to 3. And then square root 2. How much is square root 2? Do you know? 1.414. So see, that's it goes down to 1. So it's similar to the floor function. We call it floor function when our non-whole number goes down to whole number. It's like a whole number. It's like a floor function. It's the greatest integer function. Anytime we don't have a whole number, it goes down to the whole number. So from one whole number to another whole number, from one integer to another integer, it's a straight line. From the second integer to the next integer is a straight line. So we don't have anything for decimal between two integers. So for every integer to integer, it has the same value. Now, what is the limit x goes to 3 of this function? X goes to 3. So this is our x goes to 3. When x goes to 3, what's the limit of this function? Great. How do you know?
If you approach it either side, like if you approach it to like the 2, it would go to like 1. If you approach it to the 3, it would go to 2. So like if you approach it positive.
So if you go to 3 from the left side, So from left side, it has this portion.
We go to 2, from the left and go to 2, and then to the right.
But when you walk from the right side, see, this is the portion of the graph on the right side of 3. It's going to the 3. So the left limit is 2, the right limit is 3. They have a jump, so limit doesn't exist. The answer is D and E. I believe in the homework you have more questions like this on this function, greatest integer function. They're fun questions. So try playing with the homework, okay? You have unlimited attempts. So whatever you want to try, you can always try them. You don't have to worry about that. Next, they give properties of limit. So first one is saying if two functions are same, f of x and g of x, they're same. When x is not equals to a number, then the limit goes to the limit going to the same number, they give it the same y value. So if two functions are equal, their limit will give you the same y value. The limits are equal. Second function is saying if one function is always bigger than another function, then the limit for the bigger one will always be bigger than the limit of the smaller function. The interesting one is the squeeze theorem, the last one. Squeeze. It's called squeeze theorem because we look at the limit of the function that is being squeezed by two functions. One is on the left, one is on the right. So this is saying, let's say you have a function in the middle, which is smaller than the bigger one, but the bigger than the smaller one. It's in the middle, okay? Like the middle child. Let's say you have a middle child in the family, and you have one bigger, one younger. Now, the limit for the bigger one and limit for the younger one, if they have the same number, then the middle child will have the same limit. Okay? So if one function is between two functions, and the upper function and the lower function have the same y value for the limit, that means the middle function will definitely have the same y value for that limit. It could be a number, any number. I think infinity doesn't make sense here. Yes, so if the upper limit is a number, the lower limit is a number, then the limit for the middle one must be the same number. Now let's do something with trigonometry. Do you guys like trigonometry or hate trigonometry? Which one? Like? Don't like in the middle? I actually love easy trigonometry. Trigonometry could be hard or could be easy. The beginning level is easy, the middle level is easy. The hard level, I don't remember the hard level. But yeah, I hate the hard level, but the middle and the lower level is fun. So here we have a function sine 1 over x. As you know, 1 over x when x is 0 doesn't exist, right? When x is 0, 1 over x doesn't exist. So we are looking at what happens if a function sine of something doesn't exist. So the graph looks like this, sine of 1 over x. So on the side, it goes smoothly on both sides, but around 0, it goes up and down, up and down, up and down like crazy children. Okay? Like it's bouncing up and down, up and down, up and down. Since it's bouncing up and down, up and down, up and down crazily, we actually don't have a specific y value when x goes to 0. That's why sine 1 over x doesn't exist the limit when x goes to 0. But the limit exists other places, like here the limit exists. Everywhere else the limit exists, but near 0 the limit doesn't exist. So why do we care? Well, we care. Oh, are you guys done covering the properties? Do you need help? Do you need more time? You do? No. So why do we care? Because we're going to use this to find out a limit where limit of a function that does exist. What is the highest math you took in your high school or you're taking? Pre-calculus? Anybody already took calculus in high school? You did? Are you taking it or you took it before? Took it before? How was it?
At first, it was get the elevation.
True. I remember my time, like beginning it was so fun, and then they introduced us to Riemann integral or something, and I was completely lost. What is Riemann integral? I did not understand it until I taught this class. So when I take this class, I actually still didn't understand until I taught it. Like when I had to teach, we had to relearn stuff, and when I relearned, I was like, oh, really? It was easy. How? Why I didn't understand during my student age, I don't know. That's why people say, if you want to really learn something, teach it to someone else. When you teach, you'll realize what mistake you have, or you're going to discover something new in your learning process. Do anybody still need time to copy last page? Huh? Okay. So we would like to know, we definitely know sine 1/x, the limit doesn't exist, right? Because you can see it clearly. Sine 1/x, the limit doesn't exist near 0. But what happens if you multiply sine 1/x with an x cubed x to the 8 power function? What do you think? Does the limit exist or still it doesn't exist? Just guess it. It does? Why do you think it does?
Is that
X to the 8 power. You just guess again. Okay. Anyone else has any other guesses? Well, remember the limit rules I taught you a few classes, either class 2 or class 3, that if you multiply two functions and take the limit, it's the product of the limit. Do you remember? The rule I said, if you have limit f of x times g of x, this is same as limit of f of x times limit of g of x. Do you remember? If we try to use this here, okay, so this is a warning. Do not do this. What you're not supposed to do? You're not supposed to split the limit here. X to the 8, x goes to 0, sine 1/x. If you do this, we know this limit is what? 0, right? You just substitute, you get 0. And this limit is Jannah. What is 0 times something doesn't exist? Still it doesn't exist. If you multiply, divide anything by it doesn't exist, still doesn't exist. So if you try following this rule, the answer is it doesn't exist. Okay? That's why I do not do this. Well, then how do we know that what you're supposed to do? That's why I give you the hint. Use the squeeze theorem. And you may wonder, well, what squeeze theorem tells us? Squeeze theorem says if one function is lying between two different functions, and the two different functions, they have the same limit, that means the middle function is supposed to have the same limit. So how do we start? Let's start with something baby. We know sine x, right? Sine x lies between which two numbers? -1 and +1. So it doesn't matter what angle you take, sine of any angle supposed to lie between the same two numbers. It's true, right? Sign of anything supposed to lie between the two extreme numbers, -1 and +1. Now, let's multiply everything by x to the 8, each of them. So we get -x to the 8 less than or equal x to the 8 sine 1 over x to the 8, right? I'm not doing any limit yet. I'm just doing algebra. We know sine lies between -1 and +1. So sine 1 over x must lie between -1 and +1. And we multiply everything algebraically. So x to the 8 sine 1 over x lies between -x to the 8 and +x to the 8. And now let's take the limit. X goes to 0 for each function. So limit x goes to 0, -x to the 8, limit x goes to 0, +x to the 8, and in the middle, limit x goes to the 0, x to the 8, sine 1 over x. And let's observe the end. What is the left limit? 0, right? It's basic function x to the 8. So you substitute 0 here, you get 0, our limit. What's the limit for the right function? 0. So you see, we know definitely x to the 8 times sine 1 over x lies between -x to the 8 and +x to the 8. And we definitely know that -x to the 8 goes to 0 when x goes to 0. +x to the 8 goes to 0 when x goes to 0. Now by Squeeze theorem, if the two ends are going toward the same y value, the middle function must go toward the same y value. So what's the limit of the middle function? 0. So you see, if you use the rule, it doesn't exist. But if you use Squeeze theorem, the limit does exist. The limit is 0. Let's see the graph. I'm curious. Make it smaller. So we have x to the 8 sine 1 over x. Yeah, it's true. If you look at the graph, this is the whole picture. And if you zoom in, the y value does tend to go to 0 from both sides. So the limit does exist. Oh, I missed that. Any question? Any comments, concern, complaint? Nothing yet? Okay, so now some trig identities. Ignore the left page, okay? That was for me if I forget, so I can see. Write down these rules, the trig limits, because these will make your life easier. it says sine of the angle divided by the same thing. The limit if it goes to 0, sine of an angle divided by the same angle is 1. Its reverse is also true. When x goes to 0, x over sine x will give you 1. And sine is friendly with tangent. So the limit when x goes to 0, tangent of x divided by x, still 1, and the reverse is also true. Cosine is always the bad one. Okay, always. So limit when x goes to 0, cosine x over x, it doesn't exist. However, the reverse does exist. It's 0. And if you subtract cosine from 1 and then divide by x, the limit exists. But if you reverse the direction, limit doesn't exist. Did you guys have fun today? In the class? Who found the classes boring? Anyone? If you tell me how it was boring, then maybe I can help you to have more fun later in future classes. So anybody found this class boring? Not really? See, 7:20. I didn't even know how time flied. Time flew by. Huh? Say it again. Homework. We have homework 1.3, 1.4, 1.5, 1.6. Look at all the homework and do the questions which will be covered in class. The topic we covered in class. Oh, the lumen. Oh, sorry. So you go to, our syllabus. If you go to our syllabus, it has a direction. If you did not sign in, if you did not register yet. Did you register on lumen? Okay. Then take a look at the homework on every section, okay? 1.2, 1.3 to 1.6. Because I covered something from each section. So you can do some homework from each section. Okay, now, before I go, let me just show you something cool. So this is the picture of sin x over x. As you can see, near x, the y value, both are going toward 1. So our limit is 1. When you flip the order, x on the top, sin x on the bottom, this is the picture. Okay? Something totally different. However, near 0, our y value is still 1. That's why the limit is still 1. For tangent, this is tangent x over x. So this kind of similar to that. Similar, not same. Only the middle part is same, the rest are not same. But near 0, both sides are going toward the y value 1, so limit is 1. When you reverse the direction, x over tangent x, the other side is different, but near 1, still near 0, the both y values are going toward 1. So you still have 1. So sine and tangent, they don't have any problem. If you reverse the direction or if you have the same thing, you get y value 1. So limit is 1. On the other hand, look at cosine. Cosine x over x, this is the graph. And as you see, when x is 0, the y value doesn't exist. So that's why the limit doesn't exist here. The one side, the right side is going up, the bottom side is going down. You have two different limits. When you have x over cosine x, this is the graph. Now, in the middle near 0, we do have a continuous piece. So the left y value is 0, the right y value is 0. So that's why the limit here is 0. Now for the other function, 1 minus cosine x over x, it's a continuous function, so its limit is 0. Near 0. But when you reverse the direction, the bottom is top comes to the bottom. Now you see, this is the same scenario as this one. we have a vertical asymptote at 0. So that's why the limit doesn't exist, because one side is going up, the other side is going down. Okay? So keep this in your mind. We are going to use them to do this type of questions. Trig limits. And these are fun limits, okay? Fun trigonometry, not the harder one. Once you're done with this, our next class, remember, Monday will be online, so we're going to go over all of these. And then Wednesday, we have no class. And then the following Monday, we have another online class. So see you guys Monday online. Have a good weekend. Enjoy your classes in your school and enjoy doing the Lumen homework. If you have any question, you can email me anytime.